based by which you can give neutrino mass. This was some of it last time, but let's start all over again, and I'm going to try to make it perhaps better than last time. So let's see how. Anytime we hear things again, then we can make it easier. Okay, so at this point we were okay. So in lecture 13, when in the end of lecture 13, we had seen that all the fermions, like quarks and charged leptons, can be given masses by simply this Yukawa coupling. Okay, Yukawa coupling interaction takes after electronic symmetry breaking, then interaction term becomes a mass. Okay. Now we are trying to see whether one can give similar kind of mass term to neutrinos. Turns out that of course one can, because whatever you can do with top quarks, you can do with neutrinos. The complication that arises is that neutrinos can be given a mass which is even more than. So neutrinos can be given masses in more ways than normal particles can be used. Okay. There are specific reasons for that. So the standard mass that we saw for all quarks and leptons for Dirac mass, and here we see in detail what is this Majorana mass. The double beta decay, which is neutrino-less, happens to be an experimental signal by which you can check if indeed neutrinos have the Majorana mass. Otherwise, of course, nothing prevents it from just having a Dirac mass. So this will be an experimental test to check whether neutrinos have Majorana mass. So before we go there, we try to see what are Dirac and Majorana mass. So this is to remind you of the Dirac mass again. We have interaction term, which is lambda nu, which is the new Yukawa coupling that we need to have, and L bar, phi conjugate, and U bar. This we had seen earlier. Phi will not give us a SU2 cross U invariant term. We need phi conjugate. Okay, just like for giving masses to up-type quark, we needed phi conjugate. Similarly, we need phi conjugate for neutrinos. After the break electrolytic symmetry, then this phi conjugate essentially becomes d by root 2. Okay, so I have forgotten this factor of root 2 here. 2. And this means that effectively I have a term that looks like minus m times nu L bar mu bar, and hence factor of root 2. For this to happen, we also saw that nu R has to have particular eigenvalues under SU2 cross U. It has to be a singlet, and it has to have y is equal to 0. Okay. So a singlet under SU2 and y is equal to 0. So fine. This basically solves the problem. Okay. If there were no other complications that we now count because of possible lepton number violation, this is where we will stop. Okay, we will say that there exists something called as nu R. We put that particle inside. We will introduce this term in the Lagrangian, and we'll say that neutrinos are Dirac mass. Okay, and we just stop there. And it will not teach us anything new about physics. That's it. The reason we don't stop there is one dissatisfaction aesthetically, which is that if you want to calculate lambda nu value here by looking at matrices of neutrinos and looking at the value of V and so on, we will find that this lambda nu is of the order of 10 power minus 11. This is a very, very small number. It doesn't seem to add to any new knowledge by this very small. There is some criteria that Lepton gave for natural numbers. So he said that you can have a number which is very, very small in the theory only if by putting the number equal to 0, you increase symmetry of the theory. Anyway, the fact is that if you put lambda n equal to 0, it doesn't really improve the symmetry of the theory. Symmetry is the same. Okay. Therefore, having such a small coupling constant is in force unnatural. You don't want this. Minor than this. Another thing is that once you have SU2 cross U1 symmetry, it still allows you mass terms with nu R more than just Dirac mass term, okay, which is the Majorana mass term that will come. So before we go to see how this mass term looks like, let's take a detour into this particle-antiparticle systems. So I want to make that thing more. So once you look at a fermion, we will know what the Lagrangian of fermion looks like. That looks like this term. So this is psi bar I gamma mu del mu psi minus G psi bar psi and this gamma mu del mu. And then we have minus n psi bar psi. So these three we are familiar with. In fact, the first two terms are exactly what we saw maybe lecture 13 or so when we did. So we had this as a kinetic term, and then when we had a gauge field A, we got a term that looked like this. There was there I used B, here I used A. Basically this. Lagrangian of fermion looks like this. Now we know how to get equations of motion from Lagrange. And what do we expect? We expect that when we get equation of motion of fermion from this, we should get Dirac equation. Because that is the equation of motion of fermion. So we'll use this form. So once you know Lagrangian, we take del L divided by some derivative of L with respect to del alpha psi to del alpha of that. That should be equal to simply del L by del psi. And this psi can be any field which is in the Lagrangian. Now this Lagrangian has two fields. One is psi and is psi. Okay, they have to be taken as independent fields. Okay, they don't know each other at this point. We have formed no connection between. So let's try to find the equation of motion by using this equation with psi bar. So del L by del psi bar is 0. It has no del alpha psi dependence. Okay. Maybe this should be del of del alpha psi. Okay. So left hand part is 0 because there is no term here that looks like del alpha of psi bar. So only thing that we need is del L by del psi bar. So del L by del psi bar is straightforward. So this term just gives me I gamma mu del mu times psi, which is this I gamma mu del mu times psi. The second term del by del psi bar is just minus G gamma mu mu times psi, okay, which is here G gamma mu mu times psi. Okay. Third term simply gives me minus m times psi. So I have simply used equation of motion, and this basically should be Dirac equation, which if you see it indeed is. Let's also write to the second equation now, where this is now psi. So then I have to write firstly del L by del alpha of psi. So I think I should do it more here. So let me write on Lagrangian. So Lagrangian is psi bar I gamma mu del mu of psi minus G psi bar gamma mu del mu of psi minus m psi. So let's start to write equation of motion carefully because it's important to keep track of it. The equation that we want to write is del alpha of del N by del of del alpha psi is equal to so let's be careful. This is del alpha of psi. Okay, remember I am being very careful. I have not put del mu here. Okay, I especially put del alpha here to distinguish that del alpha from this gamma mu because it is important to be careful with this. So now I want to find out del L by del of del alpha psi. Okay. Now that can happen only in this term, because I have del mu psi. But it happens only when mu is equal to alpha. Okay? So we can write down the first term. So this then del n by del mu psi will become psi bar I, okay, gamma mu. But this is give me delta of alpha. Okay. It's important to keep track of the ranges. So this is my del n by del alpha psi. Now I take derivative of this with respect to alpha. So I should do this. I did not take mu because remember, if I had taken mu, then I would have had mu appearing 3 times. And that's is equal to del n by del psi. So now this is another sequence. So then this is just equal to minus g psi bar gamma mu mu minus so this now becomes del alpha of psi bar I gamma. It is now that people say, okay, now this alpha, and now you write it as mu. This is because I have this one. But I wanted to make sure that this alpha is different from this mu. So now I can leave it to normal form. Let me see if I use alpha. So now this is del alpha of this quantity, but I is a constant, gamma alpha is a constant. So this is basically del alpha of psi bar times I gamma. Let me make it a mu alpha. So summation, so it should be. This is equal to minus g psi bar gamma mu minus a psi. So this is my equation of motion for psi bar. Note that this gamma mu has to be on this side of psi bar, otherwise it doesn't make sense. Because psi bar is a row vector, psi is a column. In order to have proper multiplication, psi bar has to be on the left hand side. What we want to see is, all our particles and fermions, we would like to see what happens when something acts on them. So we want them to act as, look like column vectors. So although this is the equation on row vectors, I can always transpose this and make an equation in column vectors. And that's a good thing because then my fermion is on the right hand side, operators on the left hand side, and that looks like a nice equation. So we will come to that. Let me just summarize this. So this was my equation when I use equation of motion with respect to psi bar. This is with respect to psi. Okay. The first equation is just Dirac equation, and the second equation is what's called as conjugate equation. So it is here is the equation del mu psi bar I gamma mu minus this. So I take my left hand side term on the right hand side, and then I get 0 is equal to minus of del mu psi bar I gamma mu minus g psi bar gamma mu minus. So this equation is exactly what I have written here. Conjugate equation is this. So this is 0. This is equal to these 3 terms, all with negative signs. So now I want to take a transpose of this equation to see an equation like this standard. So let me write the equation like this. So this is the same equation. Minus del mu psi bar I gamma mu minus this is gamma mu meter minus m sin c. Now I take transpose. Transpose is straightforward. So I take transpose of this. So this is minus I comes out. I have to transpose of this and transpose of this. So transpose of gamma mu transpose. Transpose of del mu psi bar is del mu psi bar transpose. Okay, I have done nothing great. This equation again, since I have to transpose from right hand side, first I have gamma mu transpose and then I have psi bar transpose. Okay, mu and g they don't get transposed, they are not in that. And then this is minus m psi bar transpose. So what I have got now is an equation, okay, that looks like I have some particle on the right hand side, rho vector, which is this psi bar transpose, okay, and it satisfies an equation that looks somewhat like Dirac equation, okay, but not exactly. We want to make this look like Dirac equation because we are looking for a particle which has some properties. We are looking at a particle which satisfies Dirac equation, and we want it to have certain properties like it has the opposite charge of the original particle. But right now, let's not go to opposite charge. Let's just say that this is an equation, and we want to write this equation in terms of so that it looks like Dirac equation. So what do I do? This psi bar transpose is a very strange object. I don't know what this object is. What I want to do is I want to take this object and I want to write it in some other basis. Okay. How do I change basis? I change basis by using a rotation, unit transformation. Okay. I take something, I apply unit transformation, I change the basis. So let's see what happens. Okay. Let me just take each other basis. So what I do is this psi bar transpose, I act on it by unitary matrix, which I call it as C, and I call this object as psi C. Right now psi C has no meaning. I haven't given any meaning. I just said this is psi bar transpose, and then I define something called as psi C, which looks like this. I have some idea of what this psi C should look like, okay, because we know that if psi had corresponded to some positive charge, psi bar would correspond to negative charge. We had some intuitive vague idea of this. Okay? But at this moment, I have not told you anything about it. I'm just saying that my psi C is just this transformation. Now I say, okay, fine. What I would like to do is I would like this psi C to satisfy Dirac equation by G changing to minus G. So this is a Dirac equation, I gamma mu del mu of psi C minus, that should be plus I guess. Let me just see what I have in there. The equation I want should look something like this. Dirac equation, I gamma mu del mu times psi C. I think this perhaps should be so fine. I want an equation that should actually look like this. See my Dirac equation for the particle was this: gamma mu I del mu psi minus G mu psi minus m psi 0. So for a conjugate particle, I want this side to be a plus. So this was this. So what equation I am looking for therefore is this. There should be a plus sign here. So make it a big plus sign. So what I want is that this psi C should satisfy this equation. So mass is the same, coupling constant at chain side. So what does this mean? This means that my psi c is equal to c times psi bar transpose. That's my definition. So write down this equation. So I gamma mu del mu c times psi bar transpose plus g gamma mu a mu c psi bar transpose is equal to minus m c psi bar transpose equal to 0. So what do I want to do now? I have this equation which I got simply by equation of motion. I got this equation by condition on psi c. So condition on psi c that it changes the sign of g. So now I should match this equation and this equation to see what happens. And these two equations should be the same. Okay. So now let's see what's happening. I take this equation. Okay. So let me write down the equation on the sticky. So minus I gamma mu transpose del mu psi bar transpose minus G gamma mu transpose A mu psi bar transpose minus M psi bar transpose. What I want to do is I want to match this equation with this equation. So what I will do first is I shall operate on this equation by C. So C, let's see what this thing is. So this becomes minus I C gamma mu transpose of del mu psi bar transpose minus G C gamma mu transpose del mu psi bar transpose minus M C psi bar transpose. This is what I got from my Lagrangian. Now I just copy down whatever I had here. What I want is an equation that looks like I gamma mu C del mu transpose plus G gamma mu A mu, so plus G gamma mu A mu C psi bar transpose minus M C psi bar transpose. Now these two equations should be identical. When will they become identical? The last term actually already is identical. If you look at this term, this will become identical if C times gamma mu transpose is equal to minus of gamma mu times. What about the first thing? I get C gamma mu transpose is equal to gamma mu times C minus. Okay. A mu C equal to C. A mu will see this C is in the basis of Dirac. A mu is not that. A mu is sorry. So C is in spinor indices. It's gamma mu as 4 by 4. So
I'm saying that A mu C is equal to C.
yeah, but A mu is in a different space altogether. What are those mu? See, A mu is A mu 1, A mu 2, A mu 3, A mu 0. Okay. So these are all space-time indices. Whereas C or gamma mu are just 4 by 4 matrices in spinor indices. So they will commute always. See, whenever I took this transpose was in the gamma matrix space. Therefore, I never wrote A transpose. It's a different space, so it happens independently. So, fortunately for us, both these conditions are the same. Therefore, if I am able to find out matrix C which satisfies this condition, then I am done. So, if C exists, I can do this. And now what happens? If C exists, then I write down my psi C is C times psi bar transpose. So definition of my antiparticle is this. I take psi, I take its psi bar, I transpose it, and I operate by C. This is my antiparticle. So we will need to see it perhaps in the next video. So this is what I call as matching condition. As long as I satisfy the matching condition, I have defined my antiparticle right. I will tell you what this C is. C should always exist, right? If it doesn't exist, then all these things fall. We don't know. So let's go through this thing again. So our psi C, conjugate particle, can be written in many ways. Okay. One way we already saw. It's C times gamma bar transpose. But then we know how to write gamma bar transpose. So psi C, so C times, sorry, not gamma, psi bar transpose. But we know what is psi bar. No? What is psi bar? Psi dagger gamma 0. It's transpose of psi dagger gamma 0. And this is equal to C gamma 0 transpose is gamma 0. Sorry, gamma 0 is gamma 0 transpose. And psi dagger transpose is psi star. So this can be written like this. Let me see if I have found out one more. Okay. But now remember that C gamma mu transpose was equal to minus gamma mu times C. Okay. So this can therefore always be written also as gamma 0 C times psi star. So you also see this notation. Minus. So you will see in different notations like this. Hazard and Martin uses a very confusing notation. So they are not clear about what is in particular basis and what is not. Okay, so do not use notation of Hazard and Martin. Okay, this is what I found. Last time I had to use the notation and turned out that they were not consistent with what we were listening. Okay, but this is what is definitely written. So psi C can also be written in terms of 1, 2, 3 or 4. Find various notations. Hazard and Martin uses defines psi C as C gamma 0 times psi star, which is true only in certain bases. Okay, so let's not use this at all. Actually, psi C should be equal to C gamma 0 transpose times psi star. It turns out that all the bases that Hazard and Martin uses has gamma 0 equal to gamma 0 transpose. Strictly speaking, Hazard and Martin is not wrong. Okay? However, that is not the right definition. Definition is this. So psi C therefore is this part. What we need to know for further manipulations is how to write down psi C bar. So what is psi C bar? Psi C, now we know what it looks like. Psi C is C psi bar transpose, which is psi C dagger gamma 0. Okay. So let's see if I can do this without getting into algebra. Okay. So so actually I can make it simplified by using this last version. Okay, last version looks nice. So psi c bar is minus gamma 0 c psi star dagger times gamma 0. Maybe the same thing, of course. It depends on what I find next. So this is minus. This is psi transpose C dagger gamma 0. Gamma 0 dagger is gamma 0. Gamma 0. So this. Okay. But gamma 0 square is 1. So this is equal to minus psi transpose. Okay. So you see that's what I thought of. So these are you could have derived by yourself, but it's just good to know what is psi c and psi c bar, because that's what I feel in all our equations. With me so far. It's also useful to know some properties of C, which are this charge conjugation. It's often called a charge conjugation operator. It should be called a CP conjugation operator. But it doesn't only change C, it changes even parity. So this C will take a neutrino to an anti-neutrino. It will take a left-handed neutrino to a right-handed anti-neutrino. Remember it's psi bar, right? You want to take psi to something to take psi bar. Psi bar has opposite side. Okay, so often you will see that C is called a charge conjugation operator. It's actually a CP conjugation. Okay, just so it's unitary. C dagger C equal to 1. This we knew already. So that's one more definition. Then there was this matching condition. C times gamma mu transpose is minus gamma mu times C. This we saw. Should satisfy this condition. Okay. Third condition comes from the fact that if I take psi conjugate and I take its conjugate, I should get back psi. Okay. So again, if I can do it for this, let me see. So I want to take psi conjugate and its conjugate, and I want to say that this thing is psi. Okay. So let's see what I mean. Psi conjugate. So what should I use? I should perhaps use this. Psi conjugate is minus gamma 0 C times psi star. This is my psi conjugate. Now I want to take its conjugate. So this one I do. Conjugate is like doing minus gamma 0 C times the star of this. So star of this is minus gamma 0 star C star psi. Okay. So let's see what this is. Okay, so this is minus sign goes away. It's gamma 0 C. Gamma 0 star is gamma 0 transpose. Because gamma 0 is hermitians. Gamma 0 dagger is gamma 0. And C star times psi. Okay. But now we know that C times gamma 0 transpose will be gamma 0 times C, the minus sign. Minus. This will become gamma 0 C star times psi. This is 1. So which is equal to minus C star times psi. Okay. So therefore C star should be equal to minus 1. Okay. So algebra, we can go through this peacefully and convince also that is actually. So therefore C dagger C has to be equal to minus 1. Now C dagger C is 1, C star C is minus 1. So C dagger is minus C star. So C is equal to minus C transpose. So C is antisymmetric. So what we have found is that our C should satisfy these 4 conditions. And the question is there a matrix that satisfies all these 4 conditions? The answer is actually yes. And in fact, in the standard basis people use, so Dirac basis or chiral basis, blah, 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 C is simply given by I times gamma 2 times gamma 0. In this class, I don't want to go through different bases and so on. But, go to your whichever favorite book that you use for gamma matrices. See the Dirac basis. Look at the values of gamma 2 and gamma 0 there. Multiply them. You will get a matrix to satisfy all these 4 properties. I will ask you to check that in one of your assignments. So,
is that the only option once you choose a basis? In Dirac basis, this is the only C?
I haven't thought about this, but perhaps yes. I have got 4 conditions.
So you've got 4 conditions and how many?
It's a unitary matrix.
16.
So not just 4, there are more than 4 of course. These are already 16 conditions unitary. Then I have this antisymmetric. So I haven't done the counting yet. So we will try to find out if there is something identical. I suspect that C should be fixed up to a phase. Of course, phase is not fixed. If my C satisfies this, I can just multiply by e to the power I alpha, which satisfies everything. That is not fixed. So this is the proper definition. Then we can ask this question. This is something we saw the last time. It's when can the particle be so antiparticle? And the answer was, firstly, particle cannot be antiparticle unless G equal to 0 for all gauge groups. Therefore, this has to be singlet under all gauge groups we have. At SU2 unless under U1. Secondly, if particle is charged under a global symmetry, like fermion number, Lepton number, then if a particle is charged Q, antiparticle is charged -2. So, not good. So, therefore, as long as the symmetry is conserved, particle cannot be its own antiparticle. So, 2 conditions needed. One is for gauge symmetry, one is for global symmetry. Mu R happens to be special particle because it is not charged under a gauge symmetry, which was very important. It's the only particle that we have. Everything is not charged. So, we cannot do this very quickly. And if Lepton number is not conserved, then even the second property doesn't apply. Lepton number is conserved will imply that nothing can happen, but if it is not conserved, then this can happen. So if Lepton number is not conserved, then my mu R can be its own antiparticle. This is something that we went to last time, so I will not spend time. You see, Lepton number in principle can be violated in the standard form. And the caveat is that although I say Lepton number, actually what I mean is B minus N. Fermion number minus Lepton number. The reason is because non-perturbatively there exists a solution of the electroweak field equations called as fermion. This fermion has fermion number is equal to half, Lepton number is equal to half. Therefore, if you have a Lagrangian, okay, well, there is a lower Lagrangian here. No, assume you have a Lagrangian interaction term, and you put the fermion, then B is equal to half, L equal to half. So this term will always violate B symmetry and L symmetry. And we can't do anything with it. This is perfectly allowed, and therefore you can have violation of B and L in standard mode. What fermion cannot do is it cannot violate B minus L, because it's a particle with B is equal to half, L equal to half. If B is half and L equal to half, then B minus L is 0. So it turns out that even this strange solution of our Lagrangian, or big Lagrangian, his solution is hidden somewhere inside it.
Is experimental form?
Not experimental. It's a solution. Solution, therefore, it has to exist. all solutions of this exist. Right? Fermions exist, hits presumably exist, so it should exist. But no, you don't see a spinor. It's an instantaneous solution. So it's a global solution, not a local solution. It's not a particle that you find in a This is a field configuration that exists all over space at the same time. So it's a very different beast than what we are used to. That's the reason I'm not going into this. If you want to go into this, here is the reference. You can try to read this way. Given sufficient time, it's understanding. Okay? But it's a complicated. It needs time. Okay. So anyway, whenever I will say anything in the class, I will often use the word lepton number conservation. But whenever I say lepton number conservation or violation, I basically mean B minus L conservation or violation. So this is just a kind. So now that we have allowed lepton number to be violated, what can we do? We can allow a term that looks like this: MR, which is number, mu R CP conjugate, mu R C times mu. So this obeys SUL, okay, because mu R is the SUL singlet, SU2L singlet. So no problem with it. It obeys U1Y because Y is 0. Y is 0, so obviously it violates lepton number by 2 because nu has lepton number equal to plus 1. So nu conjugate has lepton number equal to minus 1. So nu conjugate bar is lepton number equal to plus 1. So this term has lepton number equal to plus 2. So if this term is in the Lagrangian, you will violate lepton number by 2. Right? So Majorana term always violates lepton number by 2, not by 1. It has to be 2. This term is what one can call as Majorana mass. So this is what we call as Majorana mass term. Strictly speaking, we write this term as minus half MR times mu R C bar mu R plus mu R C. Salvation conjugate. Okay, so you will see it either in this form or in this form. Okay, so both are the same forms. So once you have this term, then we can look at mu R plus mu R C. Mu R C is antiparticle of mu R. If you take a combination mu R plus mu R C, and if you try to take its complex conjugate, or this CP conjugate, to be precise, it will be itself. Because CP conjugate of mu R is mu R C, that of mu R C is mu R. So it stays the same. Mu R and mu R C satisfy the same Dirac equation, okay, because there is no coupling constant G. So I can do this for mu R, which I could not do for electron. So therefore, this mu can be called as Majorana particle. Majorana particle means a particle which is more than a particle. And now one can see that this expression that I have written on top can be written simply as minus half times MR times mu bar mu. So this is simple algebra. We saw how to handle this LR kind of multiplication. So if you do mu bar mu, then you will turn out that only term that here is. So this we had seen yesterday, or last time. We should be. Yeah.
So if we can write it this way, then we will call it Majorana particle because we know nu is linear plus nu is in the left-right language, nu is linear plus nu bar.
No, my nu is this. I'm not defining.
We are defining nu in this way.
Yeah. So this is the Majorana particle. This has nothing to do with our neutrino that we see. It's only about writing a neutrino. I have not yet talked about Majorana mass for our neutrinos. Okay. This is just something that I see. If you don't like it, you will go in N. Okay. Sometimes people even do that. Depends on what you like. So this U, you can call it N is equal to U R plus if you get confused with it. Okay. But this is very different. I defined it as U R. So Majorana mass term therefore looks like this. So this is again a subtlety which you have to see, because now we will see what happens to our Lagrangian when we add a Majorana mass term. This is a kinetic term which is nu r bar I gamma mu del mu times nu r plus nu r c bar I gamma mu del mu times nu r. But now you see a particle is its own antiparticle. Okay. So therefore these two are talking about the same field. And therefore, since we don't want double counting, we have a factor of half. So if this was a Dirac particle, you would just have had this first part. So Dirac particle would only have this. You will not have the second term, and you will not have a factor of half. Okay. So this is the matching of degrees of freedom. So either you write the Dirac term for Dirac particle, which is nu bar I gamma mu del mu times nu, okay, or you write nu and mu c separately, but then you need a factor of half. So similarly for this MR, that's the reason why we have this factor of half in front. When we had simple fermions, the term that we had in Lagrangian was minus m psi bar psi. Now we have minus half m URC bar. And this is again we want to avoid double counting, and therefore this factor of half comes in. This is again a subtle thing to be kept in the back of your mind. So if I combine this into nu, this simply becomes half nu bar I gamma nu del nu minus mr times nu. So this again looks exactly like the standard Dirac particle nu. However, this nu is not a Dirac particle. Dirac particle has 4 components. This information content is 4. It is the freedom of 4. For Majorana particle, although there are 4 numbers in your spinor, they are related because psi is equal to psi c. So all these 4 are not independent. Only 2 are independent. So the degrees of freedom actually are half. So Majorana particle is in some sense a half Dirac particle. Okay. Therefore, the Lagrangian will become this, the factor of half. It's exactly the same thing, right? So you can take Hermitian conjugate, but if Hermitian conjugate is going to give you the same term again, you are double counting. You want to avoid double counting. Right, so here I have not written my HCF. This is again just a curiosity which we might use perhaps tomorrow, maybe not. See this term which is nu r c bar nu r. You can write it like nu r transpose c dagger times nu r. Because nu r c bar we saw earlier, right, is just equal to minus of nu r transpose times c bar. So you will see in literature Majorana terms written in many different ways. You will see them written like this, which is nu r c bar nu r. So you can see nu r c bar nu r, or you can see nu r bar nu r c. They are just complex conjugates of each other, so Hermitian conjugates. Sometimes you will see them like this, nu r transpose c dagger nu r. Sometimes, which is where subtlety comes into play. See, C dagger is in this gamma metric space. No? C is sometimes loosely people also write this thing as nu r transpose nu r. When you see nu r transpose nu r, this means that this C dagger is implicit, it's assumed. As long as you don't do any gamma matrix algebra, this is okay. Okay, but this is not correct. It's you can call it a convention. It's a confusing convention, but it's seen very often in literature. We use this when by nu r, okay, we do not include all the spin degrees of freedom. Okay, when we are not talking about spins. See, for example, when we talked about neutrino oscillations, we never talked about neutrino as a spinor with 4 indices. because the gamma matrix, the spiral nature of neutrinos, doesn't appear when they oscillate. It's an independent thing, so you forget about it. In that context, whenever you talk in this context where the spinorial nature of neutrinos doesn't come into play, we can sometimes write a mass term as mu r transpose mu. Okay. So tomorrow's class we will see some examples where we write mu r transpose mu. So tell you what is transpose mu. So one has to be careful about this. Okay. Now the next question. So we saw that mu r has a Majorana mass term. We wrote down this Lagrangian. What does it have to do with us? Because we haven't seen mu r yet. We only know mu n. So question therefore should be, can mu n have a Majorana mass? I told you that Majorana mass term is forced on mu r. If you have a mu r, you have to have Majorana mass term. What about mu n? Because mu n is what we see in the laboratory. So that should be our question. So I can try to write it out terms that looks like mn mu n c times mu n. Mu n c bar times mu n. Okay. Now clearly this varies Lepton number, P-n number by 2. Okay. However, this does not obey SU2L. You will agree with me? Okay. This is doublet. So this is a doublet, this is a single. SU2L is not. It does not obey U1. So because
What is the single?
Oh, sorry, I'm sorry. This is doublet and doublet. However, it is still not obey C2L. A simple thing is to take U1 by. Maybe that is a simpler argument. Sorry, I was trying to give an argument. So take U1 by. Okay. For mu n, what is the value of U1 by? Yes.
That is plus 1.
Exactly, let me see. Because y of un. Okay, one can find out y of un, right? How does one find out y?
Charge is equal to E plus I by 2.
Y plus
V by 2.
this T3, right? T3 is y. T3 plus
Y by 2.
T3 plus y by 2. Okay. So charge is minus 1. So charge is 0. I'm sorry. Yeah. Is equal to T3 is plus half. Okay. So y should be equal to minus 1. Okay, wonderful. So mu n y is minus 1. So if I write down y, mu n is minus 1. Mu n conjugate plus 1. Mu n conjugate bar minus 1. That's 2. Not 0. So U1 is not obey. So clearly standard model will forbid us from writing a term that looks like this. So either you give up and don't try to give it Majorana mass term, or you think of something else. You remember that this still obeys U1 cube because no charge under electromagnetic. Okay. Therefore, if we are talking about something after electroweak symmetry is broken, electroweak symmetry is SU2 plus U. We know that Higgs breaks electroweak symmetry. So once you have symmetry breaking by Higgs, you no longer satisfy SU2 and U1. You only satisfy U1 cube. So therefore, you can have effective Majorana mass for UN. However, that is only after electroweak symmetry. So it is certain point. Mu r can have Majorana mass anytime. Okay? You can't prevent it. Okay? For mu l, you can have effective Majorana mass only after you break electroweak symmetry. This will need something beyond standard model because we don't know how to deal with mass by simply the current number of particles. So you have to come up with some new mechanism, that is true. But with the mechanism, you can have a term that looks exactly like the Majorana term we had earlier. So you have half ml mu L C bar mu L plus mu L bar mu L C. So looks exactly like the mu R mass term, but it has a very different origin. In fact, tomorrow's class will spend in figuring out what can be its origin. But it doesn't have a simple thing like mu R. In mu R, Majorana term has to be there, you can't escape. For mu L, you can give it a Majorana term if you introduce some new particles. If you leave mu L, you cannot do it. But once you do that, then exactly the same things happen. You can have mu L plus mu L C. It can be through an antiparticle. Then you will call neutrino as a Majorana particle. And you can write the Majorana mass term as minus half ml mu bar mu. Is this part clear? So you need this electroweak symmetry. Something should break SU2L, something should break SU1. Then only you will have Majorana. Only saying that Lepton number is violated is not enough to give mu L numbers. It's enough to give mu R numbers. So till now we saw three kinds of mass terms for neutrinos. We saw you can have a Dirac mass term. Dirac mass term looks like lambda nu times V. So how much can it be? You know what is V? V is 246 E. And we don't want coupling constants to be more than 1. So therefore, the MD term should be less than 200 GeV. If we want neutrinos to get mass only from Dirac, then it should be 10 power minus 1. We will see tomorrow how it's possible to have this MD as high as 100 GeV. So it's possible to have MD 100 GeV and still have neutrino mass equal to 1 electron. So we'll see it tomorrow. It's what's called a seesaw method. It's possible. But right now, independently of what we have measured, let us see from a theory point of view. From a theory point of view, this MD has a mass less than of the order of V. So which is less than of the order of 200 GeV. What about MR? MR was a term which was MR, mu R C bar mu R. And we said that nothing, there is no other restriction. Lepton number should be violated. Okay. So once you violate Lepton number, that's it. Then it can have any mass. So this mass can be as heavy as M Planck in principle. There is no other scale. Or one can say that there is some kind of scale at which you violate Lepton number. Then you call Tata as a scale. But in principle, it has no restriction. So it can be very, very high. For 10 power 10 GeV, 10 power 15 GeV, 10 power 19 GeV. At this point, there is no restriction. So in general, MR is always much greater than MT. In principle. Whereas NL, which was left-handed neutrino mass, depends on the theory. Because we said that UL must get a mass to some new physics. Unless you tell me what the new physics is, I cannot tell you what its mass is. But this new physics cannot be very high scale because neutrinos do not get a mass till electroweak symmetry is broken. Right? So at a very, very low scale, neutrinos get a mass. And that tells you that normally this Mn is much smaller than V. All these are handling arguments. The thing is congruent. Nothing will, sky will not fall down if any of these is violated. These are sort of guesses to keep at a second. So Mn is something which is very basic. And what we are interested in out of all this is basically Mn, because Mn is what we are able to measure. Others we will not be able to. So what? MD, yes, sorry. So it's also true. So an MD is something very interesting. But then only that MD should be very, very small, which is of the order of 1 electron. Beyond that, MD is forbidden. So what we will concentrate on now is to look at Mn first. How to measure Mn. Before we go there, let's go to, I'll quickly use some implications of Majorana mass. We will not go into this, but it's good to see what Majorana mass essentially means Lepton number is violated. So once you close have Majorana mass, Lepton number is violated in all your theories, so you cannot prevent it from being violated. Then you can have many interactions, many reactions which violate Lepton number. So for example, you can have processes that look like this, for example. Okay, so mu acting on nucleon. See what this is: mu plus L minus X. X is any particle. So what has happened now? This left hand side has Lepton number is equal to +1. Right hand side has -2. Okay. So X is only hydrogens. Okay, X is only. So you can have processes like this. So if you take a muon beam, hit it into a target, and you see a reaction where you see, for example, mu plus mu minus. Then you are shown the Lepton number is high. Or you can have a reaction which is mu minus E plus going to mu plus E minus. Okay. So here also, although the sum of Lepton numbers is the same, the muon number and Lepton number is valid. And one can show that at high energies, you can't see oscillations in this process. Okay, so therefore, if you see this process at colliders, this can happen only when Lepton number is valid.
You can't violate it at the Feynman diagram. You still can't violate it at the
With new physics, yes.
You can.
Yeah. With new physics, yes.
So you can have
The
some
standard
weird
model
vertex.
doesn't allow you to do that. But new physics can.
So some weird vertex you can.
You introduce new particle which has certain properties and you violate it. As long as you consistent with your current data, you are fine. Nothing prevents you from adding a new particle which violates the there are some class of models which predict some new particles called as Majorana. Let's not go into. And this is again something that I will perhaps come to at the end of this lecture when I talk about neutrinos in cosmology. That if you want to create baryogenesis, which is we have more particles and antiparticles in the universe. So to achieve that, we will need some heavy Majorana. So all these will come as applications of having Majorana application with consequences. We'll see some of them in the next classes. I'll comment on some of them. But what we'll see in the rest of this class is something that we can see in the lab today, which is this reaction called as Neutrino-less double Majorana. Okay, so let's look at what this process is. So simple beta decay is this top process, right, on top of this line. So you have neutron, going to protons, electron and neutron. That's a normal beta. There are some nuclei where it is energetically more favorable, okay, not to have just single beta decay, but a double beta decay. Which basically means that your nucleus at the same time gives out 2 electrons and 2 antineutrons. Okay. Or you have inverse also, you can give out 2 positrons and 2 neutrons, both kinds of. These are called as 2 new beta or 2 neutrino double beta. These are also reasonably rare processes. They are not found. Only a few nuclei have these. However, it is in principle possible to have a process where no neutrino comes out. So this nucleus decays by giving out 2 electrons, but no neutrino. It's called 0 nu beta. So in terms of this diagram, what it would mean is that you have this electron coming out, this electron coming out, but somehow this nu bar and this nu bar annihilated themselves inside the nucleus itself.
Possible when there is the nu and when there is nu bar.
Right. So in principle, yes. Okay. However, now we have this possibility that neutrino is Majorana. It would mean that it can be its own antiparticle. So nu is equal to nu. So it's correct. In principle, I cannot just take this line and connect with this line because nu is not equal to nu bar, it's from the same line. But now that we showed that neutrinos can be Majorana particles, this is possible. What is the experimental signal of this? The signal is very, very simple. If you look at this process, earlier one, 2 nu beta beta, you have 4 particles coming out. Nu bar, electron, electron. The 2 nu bars are lost, you don't measure them. You measure in 2 electrons. If you measure energy, sum of the 2 energies of 2 electrons, you will get a wide spectrum because some energy is given to the neutrinos which go out. In this process, you only have 2 electrons, no neutrinos. What this means is that the difference in the masses of X and Y simply come out as return energy. So which means that you just get this peak. If you look at the sum of the energies of these 2 electrons, it will be constant. So therefore what you want to do is, you want to look at a decaying nucleus X that goes to some decayed nucleus plus 2 electrons, and the sum of the energies of these 2 electrons is a constant. So in principle, the signal is very clean. You don't have to deconvolve or anything. There is some Q value. Q value is difference in the masses of parent nucleus and daughter nucleus. Q value should be entirely in the electrons, no neutrons.
Why?
It's a spectrum, so number of units.
So it's very rare.
It is a rare phenomenon, yeah. So, right now I haven't told you about nucleus.
How do you know how high the rate is in comparison to the?
I don't know. Just 2 lines that I've written on. This is no, I mean, this has not been measured. So 0 nu beta beta has not been measured.
So you might have such a deep signal there that it might even be lower than what you would expect from this graph.
Will come. Actually, why? I will explain it. The first thing you want to see is what is the amplitude of this process. So, this is the process. So this is a neutron and goes to proton. This is W. Electron going out. Another electron going out. W. Neutron coming in. Proton. So this forms a nucleus. Parent nucleus. This forms the daughter nucleus. So how do we calculate this? Let me write it down again. So E minus W. Okay. This is the neutrino. The first thing to note is the following, which is actually what we noticed, right? So this is W coming in. So this E the lepton current is going like this, E minus is going like this. So therefore the neutrino should be traveling like this. At this vertex on the other hand, you have a leptonic current going like this. So you think that, so this is EL going like this, this new L should be going like this. Whereas here you have EL going like this, therefore you would think that a new L should go like this. Okay. So therefore you should somehow have a particle which has both new L going in this direction and in the opposite direction. Which basically means new L going in this direction, which is equivalent to new L going like this, and new L conjugate going like this, and EL conjugate. This is fine, right? EL going out is the same as EL conjugate going inside. EL conjugate is EL antiparticle. So it's like electron going out is same as positron going inside. As far as calculating amplitude is concerned.
This end should be neutron by proton terminal and also proton terminal.
No, these are different vertex, right? I cannot write. Neutron protons are somewhere here.
Yeah.
See, it depends. Like whatever I do with these vertices has nothing to do with whatever I do here. I have separated this part as a nuclear part. This is what is called a nuclear matrix element. Whatever happens on this side here is nuclear matrix element. So this is nuclear physics. Okay? Which is what I don't understand. This part is electronic physics. Okay? Which is what we understand. We have to separate these two. So let's only look at electronic physics first.
So from here double charge.
Yeah, so charge conservation is always there. So both are W minus W. W minus mu, W minus mu. Both are electrons going on. Charge is conserved. This is ELC coming in. ELC is positron. Okay. So no, mind it. ELC. No, C goes to antiparticle, CP-conjugate. Okay. So left hand electron gives right hand positive. So this diagram is the same as this diagram. This equivalence has nothing to do with Neutrino physics. This is when you draw Feynman diagram, this is always true. Okay. In fact, you need to do something like this because when you write Feynman amplitude, you need electronic current to start from one point, fermion current to start from one point and travel in one direction, because that's how you write down your amplitude. Okay. Very often you don't write as E and ELC in Hazelmetal language. Hazelmetal will write this EL as U, calls U of T. And ELC it calls as V of T. Okay. So that's the Hazelmetal notation. However, for our sake, it's easier to call this an EL as ELC because now we know what a conjugate point is. Now, how will I write down this amplitude? It's very simple. So, I start from this end. This is EL bar. EL bar, EL going out. At this point, it is gamma mu. Okay, because this is W. W is W. At this point, it is nu L. That's our vertex here. Okay. What about this vertex? At this vertex, I have a nu LC coming out. So I have nu LC bar. Then I have a gamma nu, because I have a W mu coming here, and then I have a ELC coming in. So I have ELC. That's bad way of writing. Good way to write is that EL coming in is EL. Okay. I have just changed the bars to one bar, otherwise my equation doesn't make sense. Anyway, so EL, then gamma mu, and nu L coming in, nu L bar. and then I have mu L C gamma mu and E L bar. Now this looks like a nice, sorry, A L C. Okay. So this is my amplitude for the electroweak. Okay, so let's write it down again and try to simplify this. So ELC bar gamma mu ELC EL bar gamma mu. Okay. So now I have this ULC UL bar, okay, which is a propagator of Neutrino. So, but you know what expression has given UL and ULC bar, right? So this Lagrangian for UL has some factor of half, that's I gamma mu del mu minus ML. Here is L for this neutrino is half of mu bar I gamma mu del mu minus ML mu. Okay, mu is equal to mu s plus mu s. So the propagator therefore becomes 1 divided by E slash minus ml. And then I have a gamma mu here, EL, gamma mu, ELC. Okay. So this you have Lagrangian, so you can go to propagators. It's just like 1 over P slash minus L. Okay. So this I can write as ELC bar gamma mu P slash plus ml divided by E square minus ml square gamma mu times. Okay. So P slash square is P square. Now, so let's look at these two terms. Okay, this is ELC bar gamma mu P slash gamma mu. The second term that I get is ELC dash gamma mu ML gamma mu divided by P square minus ml square. Now ml is very small. Usually your P is momentum of the order of keV, MeV. ml is mass of electron, eV also. So I can write that P square. Not very crucial. Now look at this term. EL is left-handed. Okay. When you cross gamma mu, it becomes right-handed. When you cross P slash, it becomes left-handed. When you cross gamma mu, it becomes right-handed. But what is ELC bar? It's left-handed. So therefore, this is just 0.
Can you take the mod square to be same?
Huh?
Yeah, whatever, however you.
Yeah. This is a good way to do it because I don't want to go to mod square. At this level, I can save it. Then what happens here? Left-handed. Then cross gamma mu becomes right-handed. Here it stays right-handed. It becomes left-handed and ELC bar left. So fine. So therefore, my amplitude is proportional to angle. Okay, so my amplitude therefore is proportional to ml. It has many more terms. If you want to write them down. It also has ELC bar, gamma mu, gamma nu, EL. Okay. It also has Cn sigma gamma mu gamma mu then by p square. It will also have this matrix element where you have initial nucleus X, final nucleus Y with some nuclear matrix element. I don't know. But I know that this is going to be proportional to Mn. What is Mn? Mn is the Majorana mass of the neutrino which is this. So A is therefore proportional to Majorana mass of neutrino. So if I have this process, this is my neutrino. Amplitude is proportional to mass of this neutrino. The question now is, what is this neutrino? We know electron neutrinos don't have mass. Right? So what happens? This can be either nu1 or nu2 or nu3. Does electron neutrino couple with nu1? Yes. With what strength? In terms of u, UE1. That is the definition of it. Okay. So this vertex, if it's on U1, this would be UE1. Even this would be UE1. Okay. So if it was U1 inside, the contribution is going to be M1 times UE1 square. If there was U2 inside, the contribution would be M2 UE2 square. If UE3 was inside, if U3 was inside, we have M3 UE3 square. So what you have got by this simple argument is that amplitude for a neutrino double beta decay is proportional to this quantity.
And then why are you taking electron only? Why not muon and
What is my process? What is my process? Double beta decay. Okay. If you get a nucleus that gives out 2 muons, I'll be very happy, but you don't expect it to use out electrons. You can find a person with muons going out. Then if you use a question of that, it's possible. I'm not joking. People look at such processes. Okay, not at nucleus level, but at colloidals, where you have something very similar. Because amplitude, or it's like double slit. What do you do in double slit experiment? You take amplitude when the light goes to one slit, then the second slit and the third slit. Add the amplitudes and then you square. Okay? So you have same initial and final state, different processes, you add their amplitudes. This is exactly what you are doing. Amplitude in U1 is this, U2 is this, U3 is this. Okay? So now what happens? Amplitude is proportional to this quantity. Okay? So rate of decay is proportional to the square of this quantity. Okay? The square is called as m beta beta. Okay? This quantity is called as m beta beta. So I just square this. That's it. And this square I can calculate. No, I know what are the values of m and what are the UE1, UE2, UE3. You calculate that and you get an expression that looks like this. Now, therefore the decay rate is proportional to this expression. And now comes the interesting thing is that this expression involves phi 1 and phi 2, which are Majorana figures. In all our earlier experiments, we saw that we were not sensitive to Majorana figures in all oscillator experiments. Whereas here we are. So this happens to be the only conceived experiment which is sensitive to Majorana. So this is important for two reasons. You look at neutrinos, find Majorana phases, and you see that they are Majorana masses. So in fact, which one of you is going to give talk? You are going to give it, right? So when she uses the talk, I will talk about more details about these experiments. She will talk about something. I'll just tell you what the current results are. In many experiments, different isotopes, and we have limits on lifetimes of the isotopes. Notice that all of them are upper bounds or lower bounds for T, except for one, which use a measurement. This measurement is controversial, has been so for the last 10 years. The reason is that this was a Germanian experiment. This was the signal that they got, and they claimed that this actually is the relevant peak. They claimed that they had some algorithm with neural networks by which they reduce this mess into this and you get a nice peak. However, the analysis is not accepted by their own collaboration. Only a few people from the collaboration gave the answer, and the observation is not confirmed by other experiments. People don't believe this. But it's still on record because it's published. Some neural network in this material. This one is an NN. So it's a controversial question, and future experiments will actually resolve that too. This is your last comment, and you will actually, this is what the answer of your assignment question will be at some point of time. So we saw that this MEE, okay, or what you call M beta beta, is given by this expression. It's sensitive to everything: masses, angles, and Majorana phases. So therefore, if you say that the lowest neutrino mass is some m, then you can calculate what is the value of MEE. And therefore, if you actually determine MEE, these measurements, you can put some limits on absolute mass of neutrino. So therefore, these, see, this is again, this was sensitive, as I said, not just to Majorana phases, also to M1, M2, and M3, not just delta n squares. So that's very crucial. Therefore, the experiment is very important because it gives you not two but actually three different inputs. Right? So it tells you, it confirms the neutrinos are Majorana mass, it gives you measurement of absolute Majorana mass, and it confirms that B minus N is not conserved. All three things simultaneously. Therefore, it's an important experiment. So you can ask Vivek more about this. We actually have to do some Maybe we should talk to Vivek before we do anything. So I talk more about this kind of experiments when Dirac talks, user talk about various. Right now we stop.